Now, in addition to its K-space structure, we are going to see that the space of Weyl differentials forms a vector space over the function field F, and indeed this is one-dimensional, so this is isomorphic to function field. And this will be important step in the proof of the Riemann-Roch theorem. We will use it often. And first, let me note that since this Weyl differential space is non-trivial space, as we have observed here, it is possible to choose a non-zero differential omega 1. And now our claim is that to show for every Weyl differential, let me denote by omega 2, we want to see the existence of a function such that omega 2 can be written by omega times x times omega 1. So indeed, in some sense, this omega 1 represents the basis of the space of Weyl differentials over the function field F. So since we consider the omega 1 as non-zero, let me suppose also omega 2 is a non-zero Weyl differential. And these two Weyl differentials, omega 1 and omega 2, let me consider the divisors A1 and A2 such that omega 1 is vanishing on the other space of A1 plus F. So that means omega 1 is a member of the Weyl differentials of the divisor A1, and similarly, omega 2 is a Weyl differential omega F of A2. And now for a divisor B, which we will determine specifically later, we consider K-linear maps from the Riemann-Roch space of the divisor AI plus B to the space of Weyl differentials of the divisors minus B for each AI. And we define this map as which maps the functions in this Riemann-Roch space to the Weyl differentials x times omega I for each omega 1 and omega 2. And let me a bit elaborate this map by only fixing the index I as 1, but by replacing A1 by A2 and omega 1 by omega 2, you can see that this definition first makes sense. So that means indeed we want to say that this omega 1 is a Weyl differential of the differential space of minus B. So that means x omega 1 vanishes on the other space of the divisor minus B plus F. This is true because if you consider an element in the other space of minus b plus f. So that means alpha is an adyl in the other space of minus b. That means its valuation at each component is bigger than or equal to valuation of minus p for each place p. And since we define x omega alpha plus z, so that means we want to see that alpha plus z has image 0 under the Weyl differential x times omega 1. And by the definition of this multiplication, indeed, we want to see that omega 1 of x times alpha plus z is 0. And in order to see that, it will be enough to show that this vector is a vector in the other space of A1 plus F. And this is true because if we check the VP of x times alpha, so this is already is a principal adyl, and in it we want to see that x times alpha is an adyl of in the adyl space of A1. This is true because if we check the values of or the pith components of x alpha and A1 for each place p, by the properties of the discrete valuation map, and since because of our choices x from A1 plus b and our choice alpha from A of the other space of divisor minus b, indeed we can see that this Weyl differential this, let me check. Yes, so that means x times alpha is in A of A1, so that means this sum belongs to this vector, belongs to this sum of vector spaces, and since omega 1 vanishes on the other space of the divisor A1 plus F, we can see that this is indeed 0. So that means omega, x times omega is a Weyl differential of the divisor minus b. And indeed, we can also see that phi 1 is k-linear map because phi 1, the image of x plus y, the x and y are the functions from the Riemann-Roch spaces of A1 plus b by the definition of phi 1 we want to verify the linearity. Indeed, if we consider again the definition of the multiplication of Weyl differential by a function x plus y, this is going to be again the Weyl differential by the definition of this multiplication. And since omega 1 is k-linear map, again by its definition, this is omega 1 phi times alpha. So that means for every adyl alpha, we have this equality, and indeed this shows us the linearity of phi. And similarly, the image of C times X is going to be C times the image of X, because again, if you consider the definition of scalar multiplication of a Weyl differential, and since omega 1 is k-linear by its definition, we can see that we can get this equality for any adyl alpha. So, and indeed, this shows us this equality. And now we want to see that phi 1 is injection. So if it is k-linear, it's enough to check if this kernel is trivial space or not. And with respect to this definition, if you write the definition of the kernel space of this map phi 1, indeed we want to say that, so that means these are the functions such that the Weyl differentials x or x omega 1 is going to be the zero differential, right? Because the zero of this space is going to be zero differential. So that means it vanishes on the adyl space. The kernel, its kernel is adyl space. Or more explicitly, we want to say that for which functions x, the image of every adyl alpha has zero. In this case, this is going to be zero of k. And by the definition of this multiplication, indeed we want to understand the functions such that the image of x alpha under omega 1 is zero for every adyl alpha in the adyl space. And indeed, if so, that means this omega 1 is vanishes also all space of the adyl space, and this shows us omega 1 is I mean, if it is true for non-zero x, this shows us omega 1 is a zero differential, but it gives us a contradiction or our assumption. So that means this is also possible. This is only possible when x is a zero function in this Riemann-Roch space.